Okay, so there's one more thing I want to show you. This is something that is more important, very important for later, for homework 3, and it does come up a little bit even on homework number 2. Now, I've obviously been doing these all numerically, but I want to show you something. As often is the case, if you solve something symbolically, you will notice things that you may not have noticed if you just keep on cramming in the numbers as soon as you possibly can. So let me set up my equation here. Of course, what I did in both of these cases was make sure the energy is conserved. And let me go ahead and symbolically plug in the equations here. Here, just be really careful with your uppercase versus lowercase v's. Lowercase v is speed, uppercase v is voltage. I've even seen some people put little wings on your v's, your uppercase v's. If you want, you can do that to keep them straight. I won't be able to do that, but if you can, great. So what I want to do here is basically do the same idea that I was doing here, which is solving for the final speed, and I just want to solve it symbolically. And let me show you what you end up getting. Let's make sure. I think that ends up being the solution. Sorry, I'm doing the algebra in my head, but I'm pretty sure it's right. So, the main takeaway of this is this right here. The final answer for how fast you end up going depends really only on the voltage difference. Only voltage difference matters. So I want to point out that the only thing that would affect your answer is how different is the voltage where you wound up versus what it was at the beginning. So if I'd added, say, 100 joules to each of these, so instead of 3 and 9, it's 103 and 109, it would not at all change my answer. Okay? That's a pretty powerful thing to realize, is that only how different your voltage is going to affect anything. The equivalent, by the way, in our physics 1 problems, let's say I had a roller coaster, right? And I know the initial height, and I know the final height, or some, I don't know, maybe I'm searching right there. Really, the only thing I need to know is how different these two are. What I didn't tell you is this whole roller coaster is on gigantic stilts. Okay? Does that really matter? No. It matters how different is the ending and beginning heights. That's going to inform how much potential energy I give up and how much kinetic energy I can then gain from it. So being able to scale the voltage however I please, the only thing that will affect the answer is how different are the two voltages at the beginning and the end. It's like, again, like putting a whole physics 1 problem on huge stilts. It doesn't matter. Especially when we get to circuits, for homework 3 and beyond, this is going to form a cornerstone of what we do. We're going to really stop caring about assigning voltage values to particular locations entirely. We're just going to talk about what's the voltage difference between here and here, because that's the only thing that matters. In fact, one of your devices in your lab that you will use frequently, it's called a voltmeter. It doesn't have one wire sticking out of it. You don't just connect one wire and say, what's the voltage here, what's the voltage over here. It has two wires sticking out of it. You put one over here and you put one over here, and it'll tell you the voltage difference between those two locations. Okay? And it turns out, for practical purposes, that's the only thing that matters. Okay? Are there any questions on that so far? I think that covers the effect side, and we're ready to move on to the cause side. Okay, so let's just check how much time we have left here. We got this taken care of. Potential energy equals Q times V. We learned what is the preferred behavior of plus charges and minus charges. They have different preferences in terms of the spatial regions they seek, but all seek the same goal ultimately of lowering potential energy. So where does the voltage come from? Obviously, it comes from other charges. So now we have to move on to the cause side. Let's do that. So let's talk about the voltage made by a capital Q. Let's go over here, I guess. Let's do a positive charge. Let's do that first. Plus 1 nanocoulomb. I must have been doing these notes without a calculator because I chose nano. I chose nano, which is 10 to the minus 9, because it conveniently cancels out with the 10 to the 9 that's in your Coulomb's constant. So, for instance, if I were to use my formula, KQ over R, the numerator will be 9 times 10 to the 9th times plus 1 times 10 to the minus 9th. So those go away, and I just get 9. So basically, my formula, which I can work in my, without a calculator, is 9 over R. Okay. All right. So let's throw in a couple examples. Let's find like the at 1 meter away. Okay. Well, my voltage value would be 9 over 1, so that's plus 9 volts. I guess I should have put a plus here. I can plug in, say, I don't know, R equals 3 meters, and I get voltage is plus 3 volts. So these are giving me information about what is the voltage contributed. So let's go ahead and sketch it. Here's my plus charge. So what I have found is that everywhere 1 meter away, the value contributed to the space is plus 9. So here, 1 meter away, it's plus 9 volts. Over here, 1 meter away, it's plus 9 volts. Over here, plus 9 volts. So on and so forth, plus 9 volts. And notice that what is being contributed to each point in space is no longer an arrow. It's a number. It's a scalar. So we don't draw an arrow. We just draw in a dot to signify the point, and then we write the number next to it indicating what value is being contributed to that. Now, one of the things we could do is just tie these off into and indicate that everywhere on this line, which is 1 meter away, the value is plus 9 volts. We call such a line an equipotential for obvious reasons. This is an equipotential line. So equal, potential, fancy word for voltage. So this is an equal voltage line. I guess technically speaking, it extends 1 meter out in all directions, so it's really an equipotential surface. Okay, so it's like a spherical surface. But on the board, it looks like a line. And then we can go ahead and do it again. 3 meters away, everywhere 3 meters away, a voltage of plus 3 is contributed. So I guess I'll sketch that, something like this. This is the plus 3 volt equipotential line. So we kind of draw these concentric circles, and the dotted lines mean that any part, whatever the voltage is on one part of that dotted line, it's that on all parts of it. So if we say drop a positive charge here, another positive charge to react, we can of course be the omniscient viewer here where we know, okay, positive and positive repel. So it's going to go like this, right? Right? Positives repel. If these voltage values are looking familiar, right? I used them before, +9, +3. Their cause was who knows before. Now I just showed you something that could cause them, right? Another positive charge. So again, positive charges seeking lower voltage is simply a way of bookkeeping that positive charges don't like other positive charges, right? So these two will repel. And likewise, we said that negative charges seek higher voltage, and now we can understand that simply as, okay, well, of course a minus charge would be attracted to that central big Q. So the rules that we're coming up with for how things interact with in terms of voltage, they're still no different than opposites attract, like repel. It's just a way of bookkeeping it with energy instead of with force. Okay. So there is my first cause of a voltage, and it's a positive charge. Let me explore this a little further. So V equals KQ over R. R is a distance, how far you are away, so that's always positive. That should never be negative. And so what you see then is that if there are no absolute value signs in this equation, and there aren't, then what it means is that whatever Q is, that's going to control the sign of V. So if Q is plus, then V is plus. If Q is minus, then V is minus. So what that means is that positive charges make positive voltage everywhere, and negative charges make negative voltage everywhere. So we're going to go through both of those cases, starting with the one I already have. This is a positive charge, which makes positive 9 volts here, positive 3 volts here, and then even when you get really far away, R going to infinity, when you're dividing by a really big number, what does the voltage approach? 0. All right? So let's make a drawing of this function. I'll give you a couple different options. The first one, I can just draw what does the voltage look like with distance. So R is any distance you get away from it in any direction, and it's going to look like this. It's proportional to 1 over R, so it falls off in a curved manner. It's not linear. It plunges precipitously at first, and then it starts to flatten out as you get further away. If you like, we can even sketch in the two values that we know. We knew that at 1 meter away, the voltage was +9, whereas by the time you get to 3 meters away, you've already dropped down to +3 volts. And of course, by the time you get really far away, it drops down to 0. Okay. Now, that is one way to describe it, but it's not the most handy because R is kind of generic. R is just distance away. We might actually want to put a proper axis on this. So let's go ahead and throw in a axis. I don't know. Let's make the origin, how about right here? It doesn't matter where it is. So I'll throw the origin in here. I'll throw the plus x-axis like this. And I'll throw the minus x-axis like this. So what we do is we imagine that we are walking along this axis with some special box, and that box is going to tell us what's the voltage at that point. All right? So what would this look like? I'll draw the voltage versus x. Here's plus x, here's x equals 0, and over here is minus x. All right, so let's start at minus x, okay? So I obviously didn't draw this very far, but let's say I follow this all the way back. I'm way over here, really far away. What's the voltage really far away? 0, I'm really far away. And then as I walk toward it, what happens with the voltage? It gets bigger, right? And by the time I get to x equals 0, what's the voltage value there? 9. But, of course, that is not going to be the highest voltage because my highest voltage is going to be right when I ram into the charge, right? You can look when R equals 0, when you're 0 distance from the charge, then this is going to blow up. So when R goes to 0, V goes to plus infinity. And actually, what x value should that be at? When does that happen that I'm on top of the charge? How far is this? 1. It's 1 meter. So at x equals 1 meter, I'm basically going to go right up there, basically going to blow up. And then as I pass the charge, what happens to the voltage after that? It goes back down again. It goes like this. Until I get very far away, it goes back to 0. So you can basically think of it as that there's positive voltage everywhere, with 0 voltage being very far away, and it basically spikes to plus infinity when you're right on top of the charge. It's like, I like to call it a voltage hill. Although obviously that analogy only works so much because this is a hill that is so high that it has no top. Okay? So I like to call it a voltage hill. You can literally think of it like a mountain. Just remember that it's only figurative, right? There's no extra spatial dimension. We're walking along a single axis, an x-axis. But where each value on the x-axis, or each point on the x-axis has a value that's associated with it. And that value will tell you about the potential energy there. So I like to think of it as this positive charge forms a voltage hill, and then other charges will roll up or down those hills. So for instance, we have that this positive charge went over here. What would that look like? Well, it would look like this. Positive charges like lower voltage. So they roll off the hill. You could put one over here if you wanted. It's nicer to, maybe we'll drop a plus charge at the origin. Which way would that move? It would be repelled. So once again, likes lower voltage, right? So positive charges make voltage hills so that other positive charges can get off them, right? Plus little q seeks lower voltage. So plus big Q makes a voltage hill, and plus little q wants to get the heck off it. Right? Now don't forget about minus charges, right? Minus charges like higher voltage. They go to higher voltage to get to lower potential energy. So this would be trying to get up to higher voltage. We could draw it over here, which just means it wants to go to a closer distance. Or we can draw it over here. It wants to get closer to that charge that's there, located at x equals plus 1. Now this is where the analogy starts to break down because, of course, we can imagine balls rolling down hills, but there's no such thing as a ball that rolls up a hill, is there? Well, there's no negative mass, but if there was negative mass, that's what it would do. It would be repelled from the earth, right? So we have that positive charges make voltage hills. Let's put that over here. Positive charges make voltage hills. Again, remember, if it's a positive charge, it makes positive voltage everywhere, but approaching 0 when you get really far away. So the hill goes away. Okay? So I'll do the negative charge next, but the one question that you might have, how did I decide to set the origin right here? It doesn't really matter at all. Set it wherever you feel like. Some people, they prefer to set the origin at the charge. What would that look like? It would look like this. The hill would be centered at the origin, because that's where the charge is. The only reason I didn't do that at first is because for some reason it tends to confuse students. Like they think somehow that the vertical axis is like the tent pole or something like that. Okay? You don't have to have that hill centered at x equals 0. It's centered wherever the charge is located. Does that make sense? So here I made the hill centered at x equals +1 because that's where the charge was. Okay? All right, any questions on that before I go to the negative charge, negative big Q? All right, let's do that. Let's see. So, where do I go? I guess let me just go over this. So let's have my big Q be -1 nanocoulomb. So my V equals KQ over R. And this is just going to end up being -9. So if I put in my R equals 1 meter, I'm 1 meter away, I'm going to get a voltage now of -9 volts. And if I go 3 meters away, I'll get a voltage of -3. So now my voltage values themselves are contributed, they're negative. So never mind so before I said that you could have a negative potential energy arise out of a positive voltage. Now even the voltage themselves can be negative. It's a lot of managing of signs and not getting thrown off by those, okay? So let's draw this. What does it look like? Here's my negative charge. I have 1 meter away, a -9 volt equipotential, and then further away, 3 meters away, I have a -3 volt equipotential. -9 and -3. So let's drop in let's drop in a positive charge, positive little q. I know that's going to be attracted to the central charge, right? Ultimately, this stuff just winds up with opposites attracting, so it's going to look like this. Let's say, for instance, this was a positive 1 Coulomb charge. If we compare the initial points and final points using PE equals QV, we'll find PE initial is -3 joules and P final is -9. So let's do the head check. Is that a decrease in potential energy going from -3 to -9? Yeah, so this is a decrease. It's the same decrease that I had over here. The reason why the values came out the way they did, -3 and -9 for the potential energy, was not because the charge was negative, but because the voltage was negative. So it can come from either place, right? You've got to be wary of it. You can get a negative here or a negative here. Doesn't really matter. If the potential energy is negative, you got to remember to compare it properly. right? So what we see, once again, our rule holds, positive charges seek lower voltage. That's going from a voltage value of -3 to -9. That's going to a lower voltage value to lower its potential energy. Likewise, let's say we had a positive charge. A positive charge would want to go to higher voltage. Sorry, negative charge. Negative charge. A negative charge, we already said, wants to go to higher voltage. And it will. What evidence do you need? Well, you can certainly look at minus and minus repel. Or you can compute that if that charge, for instance, was -1 Coulomb, the initial potential energy, well, you have that the negative charge and the negative voltage would cancel.